Okay, hi everyone. Good afternoon on this Friday. I'm back. Today we have lecture on GeoDBMS again. Um, Three topics I wish to discuss. Between the three topics, um, I'll have a short break. The first topic is relational algebra. Second topic is query processing, and finally a third tiny topic. It's called Python and SQL. Because well, now you know Python, this Python language, you know it from last course, and now you know SQL, and I give a small demonstration of how you can combine those two languages. I'll start with the SQL part. Well, no, not SQL, relational algebra. It's closely related to relational databases. And well, let's see where we get. So, wait. Why I'll start with explaining a bit why relational algebra is so nice. Algebras, you know from high school algebra. Most people don't like it. It's about adding, subtracting, and multiplying numbers. And now with relational algebra, we're going to do the same, but not with numbers, but with tables. And or actually relationships. And well, the difference between a table and a relationship is that in a table you could have duplicate values, and the pure mathematical relationship you can't. But in case of tables with the primary key, you don't have duplicate rows in the table, so it doesn't really matter. So what we do is in relational algebra, we define calculations on relations, and it's always the case that relations go in and relations go out. And you have operators on these relationals. And the nice part is now that if you have a SQL query, that SQL query basically can be implemented or describes a relational algebra expression. So a set of operations you can do on tables, and plus a well-defined mathematics on them. So this relational algebra gives you a sort of mapping between the SQL language and a mathematical definition. So if you do it this way, there cannot be any discussion about how SQL should be implemented or what the result of the SQL statement should be. Okay, well, if you look at this algebra, it looks kind of similar to SQL statements. And I think before I start with this whole algebra thing or this relational algebra thing, I show you a bit about algebra with numbers and how you could use algebra with numbers to do optimizations on calculations with numbers. And then if you get the idea of that, then you will see that, oh, maybe you can do the same with tables. So let me start. Here I start with an empty sheet, and then I start doing annotations. Let's see what we can do with algebra. Well, algebra is really straightforward. If you have a sum like this one, 37 times 24 plus 37 times 26. Well, this is a really easy calculation. Well, if you want to calculate it straight away, it looks quite hard, but you can, because this is an algebraic expression, you can do this fun stuff with them. And if you know of these one things that you remember from high school, I don't know the word in English actually, but you can get something out of the brackets or put into the brackets. And this time here, this is this 37, which appears twice. And this algebraic function or formula you can rewrite, and then it becomes 37 times, then you do a bracket, 24 uh, Oh wait, it should be 74. 74. Make it easier for myself. Oh, I guess I have an eraser. Let's see. Oh, this is one advantage of a real blackboard. Oh. Plus 26. And well, you get the idea. 74 plus 26 is really easy. That's 100, and 37 times 100 is 3,700. So this is basically the idea. What you do in how you can use algebra to make stuff easier for you. And this is also what happens if you do relational algebra, but then with relations. Wait. Okay, now we start. How do we get from these SQL queries to algebraic operations in relational algebra? Well, let's see here. Here we have a query. Give me all the department numbers and the salary of the employees from department research. And this would be the relational algebraic operation. And it looks a bit complicated, but it's not so complicated. The only thing they do is instead of using plus and minus and times, they have these nice things like a pi for a product or a sigma for a selection, and this sign for join. And here you recognize the table names. So what you see here, these are basic relations or tables. This is the selection operator. This is one of the algebraic operations. And here you see if you see this sign in a relational algebraic expression, then what you do is a selection, and the condition that you do in the selection, so the where part of your select statement, becomes part of your operator. Then there's a join. The join sign, well, here you see already sort of join thing. You do join on department number. And like there are all these kinds of joins, like outer joins, inner joins. You have all these kinds of relational algebraic operators, like this one for the Cartesian product. Basically no join at all. Here a join or a join with a condition. Here you see the condition and a natural join. So, and here you have the pi for projection that basically also does table in, table out, and now the table that goes out of the relation has thrown away. You throw away columns, and these are the columns that you keep. So you have projection, you have pi on a relationship, and well, that's the attributes that you keep. And then relational algebra is a bit like programming. So you have an assignment operator, this arrow, and here you put the result of this algebraic expression into this variable. And you need this assignment operator for rename operations, basically. Oh no. You need this assignment operator if you want to do multiple queries, and then there's also the R sign or the row it is you can use for renames, the S sign, and assignment operator is for creating view. Okay, well, then there are these SQL-like operators, like left outer join, right outer join, and full outer join. They have these nice mathematical signs. And then also in the relational algebra, you have sum, average, or you have actually sum, average, maximum, minimum, and count. they're all mapped to this one relational operator with the weirdo sign, and where you put the name of the aggregate function inside the operator. And then you have grouping. You put the group attributes before this weird operator. So this is basically it. If you've seen the rules in the how you translate SQL statements to relational algebra operations, then you know how to translate a SQL query to a set of mathematical operations. And you need to know a few more. These are the set theoretic operations, for example, union. You have two sets, and the union is the part that is, that is the set that is the combination of both of them. Well, how would you use that? Well, if you want to find employees that are either manager or have dependents, so if you have an or in your SQL statement, that basically means that you have a union sign in your relational algebraic statement. Here you see it in tables. If you have two tables with numbers, the union is just the union of the two. It's quite straightforward, actually. And here you see where you use it. If you have an or in your SQL statement, then it will result in a union in your algebraic operation. Well, the other operation is intersection. Well, union was all of it together. Intersection is the part which is in both of them. And basically you use that. It's quite straightforward. If you have an AND in your SQL statement, third one is min or difference, set of R minus this. So if this is R and this is S, so this part is the minus part. And again, where do you need it? If you have a query like this, where you want people to be part of one group and not part of another group, then you use minus. And this is all a bit straightforward. And here you have some rules, like you have with adding. If you add two numbers, if you add A and B, that's basically the same as adding B and A. And the same holds for relational algebra. If you have the union between R and S, it's the same as the union between S and R. And all these other rules that you learned from algebra. This one I used. This one I used before, I think. No, similar like this. So, well, basically you get the idea. You can make a mapping and division. I forget about. I'm not using it. So I skip this part. It won't be on the exam either. So, and now we get to query trees, because once you've done the mapping, then your SQL statement becomes an interesting relational algebraic operation like this. So you do a project on, and here you have brackets on a selection, and the selection is done on the join of two tables, or actually three tables. And so this is one of these algebraic expressions, and sometimes they're hard to read. And that's why you can draw it as a query tree. So here you see the algebraic expression, and here you see a tree version of the expression. And in a way, this is similar to doing what you can do in normal algebra. I'll show it if I have some space left. If you have, for example, 10 plus 1 times 4, you can make it a sort of tree by doing a plus 10, 1, times 4. And now if you want to calculate this sum, it basically works like this. You start at the bottom. I see a plus here and a 10 and a 1. Oh, maybe I can solve this one. So 10 plus 1 equals 11. So where's my eraser? So in a way, this is the way you do it with numbers, and this is basically also the way that you can execute your relational algebra statements on a computer and get your end result. So you start at the bottom and doing all the operations, and in the end, you get your well, if you do all the operations, you get your end result or your answer. And of course, like it works with nested queries, like with nested algebraic operations. You can really nicely nest it. Then only the tree becomes bigger, and size for trees doesn't really matter. And then there is one thing. Usually, if you make a tree like that, you can swap stuff, and you make sure that all the projections are, or the joins are at the bottom, and the projections and the selections are at the top. And that's called a canonical query tree. So that's basically it for the relational algebra. So as you can see, well, it's a mapping to mathematics from SQL language, and I think 1 or 2 lectures later I will discuss a bit query optimization. And what you do with query optimization is basically what you look at this tree and you see, well, oh, what happens if I swap these 2 joins? If I do them in a different order, will it get faster or slower, and make predictions? So this is basically how query optimization works. So I'm not sure yet, but most of the times, if at the exam there was always a question, transfer this one simple query, and usually the query contains joins or and selections, but no projections, and you have to convert it to relational algebra just to get the idea of how it works. Okay, this was enough about relational algebra. I'm going to have a 5-minute break, so we continue at 14:08, and well, see you in 5 minutes. And the next topic will be query processing. the computer, it's 14:08. So we'll continue with the next part. I have to restart recording again. Resume recording. Okay. We're in the air again. Okay, welcome back. Now I'm going to discuss query processing. So now you know what the query looks like, and you know how it gets translated to relational algebra. And this time we discuss implementing it, and implementing it on basically on a computer. And computers, they are these nice devices, but there's a disk inside, and you have to know about the disk to know why some queries take long to answer and some queries take short time to answer. So let's see. Basically, the problem of computers is the hard disk, and I'll show you the structure of the disk, explain what disk caching is, and discuss some caching strategies. Then we discuss table operations, how tables, what stuff you can do with an operation, and how SQL queries get implemented on these tables. Then we discuss B trees, do a bit about query execution, and finally query optimization. So this is basically a disk. This is how disk looks like in your computer, and I know most times there are as many SSD devices these days, but still, even an SSD device, it doesn't have rotating parts anymore. But it contains blocks, and so disk blocks, which are discussed later, are still very important. So what do we see here? We have a disk, and there's an actuator arm, and here's the reading head, and this is a sort of magnetic layer. There's usually many of them, and these magnetic layers are rotating really fast, really fast, a few thousand times per minute. And that means that if your data from your database is on disk, and let's assume it's somewhere on this disk, and you want your query needs the data that is over here, then we're kind of lucky, because what happens then is, well, you ask to the disk, make sure that the magnetic reader is going to read this disk block, or the part of the disk that is over here. So what happens? The magnetic reader, the head moves to the right position of the disk, and then you start to wait, and you start to wait till the disk rotated, and the piece of the disk that you need to read is at the disk head. So and that's where the tricky part is, because everything in the computer gets faster and faster and faster every day. But when I started doing computer science, I think the disks were rotating maybe a few thousand times a minute, and maybe now it's 10 or 20,000 times at most, and then you have a really fast disk. So everything on the in the computer has become 1,000 times faster, but disks are still slow. So disks really are the bottleneck of computers, or especially for databases. We have some stuff. So they rotate now 10,000 times a minute, and here you see how much time you need to wait. That basically is 4 to 10 milliseconds, and so that's a long wait. And once you have located the right place on disk, it gets transferred in microseconds, basically. So the big problem is this latency. You have to wait, and the waiting time, that's what you need to get rid of. So that's basically the idea of disks. And then is the question, how do you do that? Well, basically, the best thing is to try to avoid reading disk as much as possible. And once you start read as many contiguous blocks as possible. So that basically means if the disk block of the disk moves somewhere, make sure that all the data, or that you read all the disk blocks that are in that neighborhood, and make sure that there is interesting information on those disk blocks. And that helps you avoid waiting on disk I/O, because if you can predict what data you need, you can read the data in advance and do a sort of read ahead. And the other thing is, well, if these disks are so slow and computer memory is fast, make sure that once you've loaded a disk block from disk into memory, just keep it in memory and don't throw it away anymore. And well, there's the big problem, because usually the disk of a computer is much bigger than the memory. So your memory grows full and they have to throw stuff out again. Here again, you have this image of a disk. You have the disk head, the reader, and the writer. And here you have adjacent disk blocks, or basically, I would say these are adjacent disk blocks. So if you have a table of your database and it fits in 3 disk blocks, well, if you want to query the table and it's 1 disk block over here, 1 over here, and 1 over here, and you want to have all the data, then you need to wait 3 times. So usually it's much better to put disk blocks or data together in disk blocks that are really close to each other, because then if you want to query one table, then it goes basically 3 times as fast. And I don't know whether you remember, but I think 10 years ago, then there was this software which you got with your computer. It's called a disk defragmenter. And after you run that, then your computer became much faster. And why is that? Because also your files of your files that you store on your disk are stored in this way in disk blocks. And usually, if you write a file, then by writing it, so the operating system makes sure that it gets stored in adjacent blocks, so that if you reread the file again, it goes quick. But if your disk is almost full, or if you append something to a file and in the meantime something else happened, then it may be the case that your file gets fragmented over the whole disk, and then it starts getting slow. So a long time ago, I think now Windows does it automatically, but long time ago there were these disk defragmenters that were reordering the disk blocks for you. And this is basically a trick that still holds in databases. Because if you look at it from an implementation point of view, a table is just a bunch of disk blocks. So here you have a table that is stored on disk, and I don't know the columns of the table. There is one column here, and here you see that in each disk block, apparently 4 rows you can fit in one disk block. So then there are these tricks, like try to avoid disk access. So put together data that are needed at the same time. So what is really nice, so it's really convenient if data that you need together often is stored on the same disk block, and that there are tricks for that. And the other thing is read many contiguous blocks, so cluster them together. We discussed that already. And so that is one thing. Make sure that disk blocks are put together. And the other thing is try to make sure that the disk does not become a bottleneck. Is you try to avoid disk access, and that is by caching. And well, basically, you could have seen that while doing your exercises, but because what happens a lot is you do queries on the same table over and over and over again. And it's nice if you do the same query the second time, that the disk blocks that you need for this query, they're not stored in disk, but they're stored in a disk cache in the computer memory. So basically what happens the second time you do the query, the database is going to request the disk blocks, and then there's this disk cache is saying, well, I remembered from last time when you wanted this disk block, So I've kept it in memory, and then you get it back much faster. So usually if you perform the same query twice, the first time it takes a bit longer because the first time the disk blocks were needed to be retrieved from disk by the pager, and the second time they're already there. So this basically helps. There's only one problem, that memory in a computer is always smaller than the disk. So once you run out of memory, so once your memory is full, you have to throw away one of these pages to make space for a new one. And then the interesting question comes, which page are you going to throw away? And well, of course, you want to throw away the one that you don't need anymore, but you cannot look into the future, so you don't know that. So you try to find a sort of prediction strategy. And well, depending on the use case, many of these prediction strategies were used, and all of them are applicable or useful or the best one in specific use cases. So a straightforward one is least recently used. So if you have this cache and there's this one disk block that you haven't used for a long time, apparently you haven't used it for a long time, so my prediction is you're not going to use it in the future. Let's throw away that one. Or this one is really easy to implement, random replacement, just pick one and throw it away. Or the least frequently used, a bit more work to implement because you have to keep count on how often you use those blocks. Or sometimes even most recently used is a nice strategy. It sounds a bit weird, but there are use cases where this is useful. And again, to make it a bit more modern, everybody these days is doing machine learning. So maybe we could use machine learning to predict which blocks are not needed anymore. But this is an important part of your database, basically, the disk cache, or how does it work. So and that's why it's sometimes interesting. So if you say, oh, my database is slow, how do we make it faster? Let's buy a faster processor. No, that doesn't work. Most of the time, if you want to have a faster database, then in many cases it's better to get more memory instead of buying a faster memory or so, because more memory helps, because then the disk cache has more space to use. Okay, so disk caching is important. Now we know that. Let's see how operations on tables work. We have database tables, and how does that relate to disk blocks? Well, let's see. What's the kind of stuff you usually do on the database table? Well, databases are tables and they have records, and usually there's an operation to insert a record, to delete a record, to update a record. That's not really another operation, because an update record is basically the same as deleting a record and inserting it again. And then the thing we did most, we search a record on a specific field value or a combination of fields. And then the final thing we do a lot is joining tables. So let's start with the simplest operation. What happens in the computer if you search a table on a field or a combination of fields or whatever? Well, let's see. And let's do it on an unordered table, an ordered table, and we could discuss hash table, but we're not discussing them, hash tables, but this is a way that is very often implemented in databases, and they're extremely efficient when you're trying to implement an equijoin. So let's start with the unordered version. Here we have the table again. They're stored on disk blocks. So we have 1, 2, 3, 4, 5, 6 disk blocks. And as we know, the disk block is the bottleneck. So the only thing we're going to count here is how many disk blocks do you need to do your query. And let's see, when the thing is unordered. So select from the database where the number is 25. Because it's unordered, you have to search the whole thing, and you have to read this block 1, 2, 3, 4, 5, 6, all of it, and in the end you have no match. So this one is costing 6 disk blocks. But then inserting and deleting on this table is really convenient, because you can insert them just at the end, and you can delete them by deleting one number and then moving this. If you delete 16, you can do it in 2 ways. You can label this as being deleted, or the other thing is you can delete it by removing this one or moving this one over there. So this is unordered files. It's also called the heap files. New records are inserted at the end. You need to do linear search to find the record. And insertion is quite efficient, and searching is not so efficient. And of course, most times we do more searching than inserting. We're going to try to improve searching records. So what you could do is you sort the data file. And well, I showed it here. The same records again, this time sorted. And we do the same query again. We could do it in different ways. We could start scanning again, but no, we don't. We use binary search, and that's very often used in computer systems. How does it work? If you do binary search and you want to find the value 25, you start exactly in the middle, that's over here, and then you check this value, oh, 12. 12 is smaller than 25. So if I check on 12, I already know that the value of 25 cannot be in these 3 disk blocks. So these 2, I don't even have to read them. So I do the same again on this part. I check in the middle. Let's check on 17. Okay, 17 is again smaller than 25. So this is the second disk block I read. And I only have a look at this value, but I read the whole disk block. It's 25 is bigger, so I go to this one, read the third disk block, and okay, no, 25 is not there. So this is binary search. So each time you do your, you look at one value in the data exactly in the middle, and each time you do it, you throw away half of your problem, because or you found your data, because each time you halve the number of disk blocks that you have to look at, and that means log n. But then, so this is really efficient for searching. But if you want to insert, it's going to be really expensive, because well, if you want to insert the value 0, then you basically have to move all the data one step down, and then you have place to put the 0 there. So if you do if you have sorted data or sorted files in your database, searching is quite nice, and inserting is not so nice, or it's really bad actually. And then we go to the third way of storing it, and that's called a B tree, and that's a tree structure on top of the disk blocks. So we'll see that in the next slide, but the disk blocks are structured a bit differently. Let's see how it works. Again, you have the numbers stored on disk blocks, so each blue rectangle is basically a disk block. But now these disk blocks, they are structured in a different way, and they are structured in a tree structure, and they point to each other. So here you have again the numbers that are stored, and so basically it's still disk blocks with numbers in them, but in a different way. And this is called a tree, and each block is called a node of the tree, and these blocks, they have children. This one has 3 children, and here you have at the bottom, it's called a leaf of the tree. So unlike in biology where trees grow upward, in computer science usually trees grow downwards and they have leaves at the bottom. So this is basically a tree, and now you have to see that there's some extra structure here because these numbers are not randomly distributed, but they're in a special way. So here, if you look at the root node, here you have the value 7, and then this root node points to child number 1, and then it basically states that this value 7 can only mean that all the children that are to the left, they have values smaller than 7. And here you have value 7 and 16, and then the children that are the child that is between 7 and 16 has values that are between 7 and 16. And then again, the right child, if it has all the values over here are bigger than 16. And this is the way this tree is constructed. We're discussing how this construction works later, but just assume we have a tree like this, and then we're going to have this query, find the object where the number is 12. Oh, we started at this root node again, well, 7, 16. So we read this block, no, data is not there. But then we know that 12 is between 7 and 16. So we can go to this block, we read this block, and check all the values. Oh, 12 is there. So we found it. So if you have your data in a tree like this and you search for this value, then you would need to have access to these blocks, which is kind of comparable to this binary search. But then the nice part of a B tree is that you can update the B tree by, that means you can insert numbers, and etc. I see a question is, what happens if the value is 7? You mean, I guess, the value over here? Then if you search for 7, then what happens? Or was this question already for a previous slide? Well, if the value is 7, for this one, you start searching over here. Okay, not for here, I see. Was it on this slide, the question? No, I assume this one. So assuming that you do binary search on this one and you want to search the value of 7, then basically what happens is, well, you start in the middle again. Oh, it was the one with the B tree, sorry. So find the value of 7. Okay, I finally understand what you typed. Find the value of 7, you start at the root of the tree again, and you check all the values in the root of the tree. Oh, 7 is already there. So that one is really straightforward. So and then if you want to find the value that is not there, it also works like this. If you want to find the value of 3, oh, 3 is not here, but it has to be to the left. Let's check this block. No, 3 is not here. So this is basically how it works. And now we get to updating B trees. Well, this is kind of tricky, and I have a movie for that, but the simple values are easy. So if you want to insert a value, insert a new value in the B tree, you basically, what you do is you first find the node of the tree where it should be. So if you want to insert the value 23, let's first find out where 23 should be. 16, no, to the right. 23, oh, over here. 23 is not here. And well, this leaf is not empty, so you can just add the value to the leaf. So you put 23 here. And so this leaf is this block and there's still space. So that would be easy. But then if you would want to insert the value 3, again, you're going to find which disk block should it be. Oh, it should be over here. Oh, shit. Oh, dear, I mean. the value 3 doesn't fit anymore in this disk block. What do we do now? Well, what you basically do is you split this disk block in 2 new blocks, one with 1, 2, 3, and one with 5 and 6. And then these 2 disk blocks, they become extra children of this disk block. So this one gets an extra child. And now I'm forgetting some of the details, so I move to the animation to see how it really works. And this animation is in what was it again? I needed a special browser for it. It was in. So let's see. Here we start. If it's okay, you should hear also the sound from my computer now.
A B tree is a tree data structure that maintains a set of values in sorted order. It is often used to implement associative arrays.
This will take about
A
5
B tree,
minutes
or some variation of one, is often the data structure of choice when the amount of time it takes to access a node is much greater than access time within a node. For this reason, B trees are frequently used in databases and file systems. Nodes in a B tree usually contain multiple elements. Non-leaf nodes have one more child than they do elements. Each B tree has an associated parameter t. Every node in a B tree other than the root has between t-1 and 2t-1 elements, while the root node has between 1 and 2t-1 elements. In the B tree shown here, t is 3, so nodes other than the root contain 2 to 5 elements. All of the leaf nodes in a B tree are at the same depth. Also, the elements that may appear in a given subtree are restricted by the elements of the parent node. So in this diagram, the elements in this node are required to be between 18 and 26. Similarly, the elements in this subtree are constrained to be greater than 42. Although the B tree in this diagram contains integer values, B trees can store other types of values such as strings. A B tree can be used as an associative array by storing key value pairs as the elements of the tree and ordering the elements based on the keys. Searching a B tree for a particular element entails following the appropriate path down the tree. To search the tree depicted here for the number 82, we begin at the root of the tree. Since 82 is greater than 42, we move to its last child. After a linear search on this node, we see that 82 lies between 67 and 84, so we move to the node's second child. We do a linear search on this node and locate the number 82. An element inserted into a B tree is added to one of the tree's leaf nodes after searching for the appropriate position to insert the element. For example, to add the number 29 to the tree, we add it to the beginning of the node containing 31 and 34. A problem arises if such an addition would make the node contain more than 2t-1 elements. In this case, before adding the element, we split the node to which it belongs. To split a node, we identify the node's median element, move it to the parent node, and change the pointers to the children as appropriate. Then we add the element to the appropriate new node. Since splitting a node involves adding an extra element to its parent, the parent may itself end up with too many elements. To correct this problem, we can split the parent node if it receives too many elements. Alternatively, on the way down the tree when we are searching for the correct place to add the element, we can split any nodes we encounter that contain 2t-1 elements. In either case, it is possible that we will end up splitting the root node, which will result in creating a new root node and increasing the height of the B tree by 1. To remove an element from a B tree, we begin by searching for the node containing the element. Deletion is straightforward enough when the element to be deleted is an.
Okay, this much for B trees and inserting. This is not only important for B trees, but Professor van Oosterom is also going to discuss R trees. And B trees do not work with polygons because you need to be able to sort them, and you cannot sort polygons. And R trees are a sort of variation with polygons on the B tree. So it's also important to understand B trees, because otherwise, when the lecture is about R trees, you get a bit into trouble. So that's it. So B tree is a nice combination because now you have your data sorted in a way, and you can do fast searching, and you can also insert and delete relatively efficiently. It's quite a bit of programming, but you can do it. You can do it basically. So now we've discussed hard disks or disk structures, caching, table operations, a sequential scan for finding a data, and sorting for finding data, and B-tree structures for finding data. And now we're going to use that for query execution. And well, basically a select from where is straightforward. This was already discussed, but we're going to do a join. And let's see how joins work when you have two tables. Let's see this one. You have the employee table and the department table. This is the join you're going to implement. So this is the relational algebra. And this is the SQL query, find all employees and departments that belong together. And now basically, if you want to implement it, there's these two solutions, and that's the nested linear scan, and you use the B-tree. And let's see what happens. Well, you've done Python programming, so you understand this. If you do the nested linear scan, and for each record in employee, do the same for each record D in department, you're going to compare if the department number of the employee equals the department number of the department, then you're going to print the results, and otherwise you're going to do the next. So this is a nested loop, two loops inside each other. And if you want to predict how much time this is going to take, well, we're not discussing this structure here, but basically this loop is going to be, this compare is going to be executed the number of elements in E and the number of elements in D. Well, here in our example, E and D are not so big, so maybe this happens 100 times, or 24 times, I think. But you can understand if you have two tables with a million of rows, then this is not going to be really efficient. But this is basically the only thing what you can do if your data is in a heap. So if it's not sorted or so, this is all you can do. So and that's why most tables aren't sorted or have a B tree inside your database. Then this is called the outer loop, and this one is called the inner loop. And there's this one trick you can use. Use the smallest table for the inner loop. Why is that? Well, this has to do with caching, because it may be the case that your memory is so big that it can hold the entire table D inside your memory. And then if you do this loop for the second time, so for the second record E, and then you still have your whole table D in cache. And as we know, that saves a lot of time in getting the data. So if you do this, do always the smallest table in the inner loop, because that can become more efficient. But then usually tables are sorted, and then you have the same query again. For each record E and employee, search the B tree of department for department number, and if it's found, return the result, and if it's not found, you do the next one. So this time, well, you do not have this big explosion anymore, like the two sizes, the multiplication of the two tables, but it's way more efficient. So this is the way B trees are used in databases. And there's this tricky thing. Usually, if you have a query in a database and somewhere there's a nested loop in the query, and the nested loop is not using B trees or whatever, then you can be sure and you can predict that this is going to be slow. So whatever happens, make sure if you do a query that there's no nested loop there. And so this is basically what you do is, if you want fast databases, get rid of the nested loops and add B trees. So now, how can you see whether there's a nested loops, or how does it work? now I discussed this query optimization. We're just discussing how it is done in that it is done in the computer, and not really how it is done. So what basically happens if you send a query to the computer, it's a SQL query, it's a high-level language, so the computer parses it and validates it, and then you get an intermediate form of the query. Usually this intermediate form is in the relational algebra. Then you get the query optimizer doing interesting stuff like reordering the query operations, and that results in an execution plan. And that execution plan is encoded, and then you run the execution plan on the database. And this is the interesting part, the query optimizer, because here the real work happens, and here you go from a slow query to a fast query. Let's take, for example, this query. Again, the join is there, find all employees that are well, that work in a department where the last name of the employee starts with an A, and the department is the research department. Oh, actually, this one is you could implement in many different ways. So what you can do is make a small table by selecting all the employees with the name that start with an A, and join that one with the departments, and see whether there's research department. Or you could do it the other way around, find the department, the number of the department that is research department, and join that with the employees, and do it the other way around. And actually, the best option on what order to do it depends a lot on the availability of indices and what kind of data there is in the database. So if all persons in if all employees in this organization have a last name that starts with an A, maybe it's a family business or so, then the selectivity of this one is really low, and you could better start with this one, but it can be also the other way around. So what databases do is they keep lots of statistics on all the tables, and based on those statistics, they do query optimization. And during that, they're making a sort of prediction of how big the result of a query like this will be. And that's called query optimization. And well, this is basically outside the scope, but you're using this equivalent stuff on relational algebra. So if you two tables A, B, and C, you can first join B and C and then join them with A, but this operation is going to give exactly the same result, but it might take more or less time to calculate. So that's it. So query optimization is really important, and it's really important, especially for you if you do queries and you think, why am I waiting for the result for 1 hour? Can it be faster? That's probably because there is a nested loop there. And now the question is, how can we see whether there's a nested loop? And actually, pgadmin is helping you for that. So let's see. I copied it. By the way, I'm really sorry about last Wednesday when this pgadmin tool didn't work. Well, it turns out that this bug is really fresh because the solution that was found on the web was also from last Wednesday. But Snortje, for example, figure out you could also use other tools than pgadmin, like dbeaver.io was really nice. I'll put them in the slides for next time, but actually this is the first year that we had so much problems with pgadmin. So let's see what happens. Let's connect to the database. Let's send the query. Here we have the query, and I first remove the explain to show you that it works. Actually, the query doesn't give any results, but that doesn't matter. It does what it does. And now you could type explain here. And run the query again. And here you get this nice answer result, but actually this pgadmin has this nice option of making a graphical version of the explain. I think it is, where did I see it? I think this is the one, explain, yes. And I want everything. So here you see, how does this query get implemented? Well, it does a nested join loop on the employee and department, but it's using the primary key. So although it is a nested join loop, the inner loop of the join is using a primary key. So it's using a sequential scan on employee, and then it's using the index on the department. So this looks quite efficient. And oh yes, for the rest, if you have a table with 3 items, this doesn't really matter. But here you can see already the predictions of the cost. And now what happens if you have 2 big tables, make sure, and you use this explain thing, make sure that there's sequential scan only once. So that's the idea of doing query optimizations. And in this way, the Speaky admin tool helps you in finding whether your query is right or wrong. And then if you see that, for example, if 2 sequential scans happened, then it would mean, oh, maybe I could add a B3 index on one of the tables. So this is it for query processing. I think that was also the final slide of query processing. I have just a few slides left on mixing Python and SQL. I think I need a 3-minute break, so I'll be back at 14 hours 53, and then I do this final 10 slides on Python and etc. And then we're done, and that gives you some extra time to do your assignments, for which we didn't have that much time last Wednesday. Okay, see you in 3 minutes. Let's pause the recording. Okay, I'm back. Depending on the watch, it's 53. I guess you didn't really leave. So, final part. So, at the end, now you know two languages. Maybe you know even more. Well, it's two computer programming language, Python and SQL. And it happens a lot that I use those two languages for doing fun projects. And I'm going to show you now one project that uses a mix of these two languages. And let's show you how you could do the same for any of your own projects. So two languages, why you need two? Well, Python is a sort of scripting languages. It uses procedures and it's pretty good at making loops. And then the other language is database query language, so it's nice with languages or nice with databases. It's declarative, so you tell what you want and not how you want it. It's basically the query optimizer that decides how it's going to implement it. And SQL is good at getting the right data. So what happens a lot is that you have a Python program, and at the top of your Python program, there's a SQL statement that gets the right data from the database, and then you're making loops on that data with the Python program. And here you have it. And for Python, you need well, the easiest thing usually is to write a Python program and do your SQL statements inside the Python program. And then you need this Psycho PG2 Python module. I guess you know how to install Python modules. It's quite straightforward. And now here, if you have this SQL query, so you've seen it before, and now if you want to implement it in Python, you do a few pretty tricky things. You import this module, then you connect to the database. Here you say the host. In your case, this would be localhost or 127.0.0.1. The name of the database, usually Postgres or whatever, your username and your password. This is how you connect. All the things you also need if you connect with pgadmin. Then you create a cursor for the connection, and on this cursor, which is basically a sort of iterator, you execute your query. And then you do a fetch all. That means, well, get the result of this database, of this query from the database, and here you iterate over all the rows in the database and print all the different columns. And then you close the cursor and you close the connection, because otherwise, well, stuff goes wrong sometimes. You should forget about this. And this is basically it. And if you run this Python program, I tried it some time ago, so it's not live on my computer now. You get basically what you expect. So this is the end result of the join. So this is a Python program that executes SQL queries, and then of course I try to do fun stuff to do stuff with it that was useful or fun. And the one thing I did is, maybe you know that Google is keeping a lot of information on you. Well, especially for me, because just for the sake of research, I decided not to say no when this privacy thing about Google location question was there. So when Google asked me, "Do you want me to keep track of where you are?" I said yes, and in the end, I wanted to know, what does Google know about me? And then it becomes interesting. This is basically, well, yes, these days with Corona, my life is not so interesting anymore. And well, at the time I was making this site, it was also, I was leading a predictable life. So over here you have architecture. Oh no, over here there's architecture. I used to live over here, not anymore, by the way. Now I live here. Here's school of the children, and kindergarten is over here. So basically, what I was doing a lot. I was going to work, and then I was bring children to school, and I go to work, and then at the end of the day, I do some shopping over here, and then I go make this tour to get the children from kindergarten. So this is basically what happens a lot for me, and Google keeps a nice track of this, but doing it every day of the year. And then, of course, it's interesting to know what does Google know about me, and you have this Google Takeout, and I guess it's on google.com/takeout or so. But what you can do is download your data, especially downloading your location history, and then choose the JSON format. JSON is a sort of file format which is um, convenient, and most Python software can easily read this JSON file format. So I did this, and then you wait for a few hours, and then you get the data set, and it's a big, 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 big file that you get, and it looks like this. This is JSON. So you have timestamps. So this is a timestamp. I think this number means the number of milliseconds since 1970, January 1. Is a latitude. Well, there's 52 north and 4 east. So here you have to put the dot, do some multiplication, and there's the accuracy. I don't know exactly what it means, but we can make a guess, basically. And if you have a big file, this looks nice, but of course it's nicer to put it in a database or use a GIS system to view it. I'm not sure this is readable, but this is the whole Python program. So this Python program converted my Google location history in the JSON format to Postgres. It imports some modules, PsychoPG, and then I create a table, and then I iterate over this JSON file, and I do the complete the calculations. So I convert the timestamp convert the time to a timestamp, which is understandable. It's a millisecond, so I divide by 1000 or so. And the longitude, I have to do some calculations, etc., etc. But in the end, the data that was in the JSON format is now in Postgres, and it looks like this. Timestamps readable, so know when I did this, 2015. There's the coordinate where I was, and this is Google's guess of what I was doing. Still, this looks like a database, or this looks like this is database, and then the nice part is if you're using this this spatial, so PostGIS spatial, then that's nice because a GIS tool can read this column and make maps out of it. So I use QGIS. You also know this software, I guess, to view the data that was in Postgres, and then it looks like this. Well, basically, you're interesting or not, I don't know. But what surprised me the most is the enormous amount of data that Google has on me. This is data of a few years. Here's the Faculty of Architecture. My house used to be somewhere over here. You can see the street. I was traveling a lot. I come to the city center once in a while. So, well, this was an kind of eye opener for me, and what I liked. Well, I'm not drawing any conclusions from it, but what I liked most was that it was quite easy and straightforward with the Python program and a SQL statement to create this kind of database or this kind of data or visualization. So, well, I hope you will try stuff like this in your future career as a GIS student. And one thing, I think the next slide is, yes, I found out that since last year somewhere, Google is not only keeping my location, but it's also keeping addresses of the places that I visit. So there's even more detail now, and I haven't changed my scripts yet to include this information. So if you want to try this, please go ahead and make your day. And that's it for today. So we discussed relational algebra, we discussed query optimization, and we discussed fun stuff you can do with Python and SQL. So, well, that's it. Have a nice weekend and see you on Monday. Bye bye.